In today's lesson, we are going to be looking at the rule of sum. Now, this is going to incorporate some topics that we've already kind of looked at before, but we're going to now apply it to some of the counting and some of the permutations that we've learned about in this new unit. So just to review some of the previous concepts, how many numbers can be made from the digits 1 to 5 if A, you want a 5-digit number with no repeats, B, you want a 5-digit number with repeats allowed, C, the number must be 3 digits, no repeats, D, there is no repetition and the number must be greater than 500, and E, the number must be less than 300 and repeats are allowed. So again, take a second or two to go through, try these review questions. We can zoom out so you can see all of them. But try these review questions. I'll give you some time and then we'll pause the video and try them and we'll come back with the answers. So if we take a look at the first one, for A, we want a 5-digit number with no repeats. If we do the slot method, we have 5 spots, so then it's 5 options for the first one, then 4, then 3, then 2, then 1, or 5 factorial, which works out to 120 ways. If we do allow repeats, and that means there is 5 options for each spot or each value in the 5-digit number, so that means 5 times 5 times 5 times 5 times 5, or 5 to the power of 5 ways. For C, the number must be 3 digits with no repeats, so that means we only have 3 slots to use. So 5 options for the first one. Because there's no repeats, then there's 4 for the next, then 3 for the one after that. Or you could do 5, pick 3, or the permutation kind of notation formula. For D and E, so for D, there is no repetition and the number must be greater than 500. So we're going to assume that we're only looking at 3-digit numbers. And that means then for the first digit, it has to at least start with a 5 because it has to be greater than 500. Then for the next one, it could be any of the remaining numbers. So there's 4 remaining. And then for the third digit, 3 remaining options from there. So 5 times 4 times 3, or 12 options. For E, the number must be less than 300, and repeats are okay. So again, assuming that it's a 3-digit number, we have 1 or 2 options for the first number, because we could be 1 or 2. Right? It can't be anything 3 or higher, 3, 4, or 5, because that would make it the number larger than 3. And then because we are allowing repeats, then the remaining 2 digits can be any value. So we have times 5, or 50 ways in total. Let's put down 3 digits. So again, we have that kind of clarification. Because if we didn't have that clarification, that could be, we could have also a 2-digit number, which would be less than 300, and a 1-digit number, which would also be less than 300. So there's different things that we would have to take into consideration, and that's something that we're going to look at in this lesson today. The next one, a couple is trying to decide what to name their baby. They have 5 different first names and 3 different middle names. How many different name combinations are possible? I'm not going to worry about pausing the video for this one because this one is relatively quick. Again, we can take a look at the 3 slots. Maybe it only really talks about 2. You could put a third one in there and we'll talk about why it's not really going to affect it. So you have your first name, your middle name, and your last name. So these parents or this couple, they have 5 different first name options, 3 different middle names, and assuming that they're going to have 1 last name, you're not hyphenating it, there'd only be 1 there. So we could include it, we could not. It doesn't really give us any information about it. So we can assume that there's only 1 last name. And there's 15 ways that they could name, or different naming combinations. So the rule of sum is what we're looking at today. And so when a first action can be performed in n ways and a second action in n ways, but the 2 actions cannot be performed together, then there are m plus n ways to perform the action. right? And one key thing here, two actions cannot be performed together. So this is something where we are looking for, where we see something that's similar to mutually exclusive, where we've seen that before. And the key word that we've been seeing would be or, where you have one case or another. And then we have, there must be m plus n ways to perform the action. So we're adding in this case, and that's kind of the rule of sum. We're going to be adding cases together. So in a deck of cards, how many ways are there to select a red face card or a black ace? So in this case, we're looking at two options. A red face card, there are 6 of them. There's 3 hearts, 3 diamonds, plus 2 black aces. So there's 8 ways in total. So this is something similar. This would be something similar that we've looked at before. How many even numbers can be made from the digits 1, 2, 3, and 4? So now this is going to be a little different. There's no restriction on how many digits we could have. So we could have a 1-digit number. We could have a 2-digit number, 3-digit, or a 4-digit. So we have many different scenarios to look at here. So let's look at the first option. 1-digit number, there's 1 slot. If it has to be an even number, then that means it has to be a 2 or a 4. So there's 2 options in that 1-digit number. For a 2-digit number, we have 2 spots. Because it's 1 digit and another digit, we're going to multiply them. But how many ways or how many even numbers could we form with 2 digits? Well, in order for it to be even, it has to end in an even number, so a 2 or a 4. So there's 2 options for the last value. We could then say that how many options do we have for the first number? Well, in that case, we have 3 remaining numbers from the 4. And again, we're going to assume no repeats. So 3 options for the first number times either the 2 or the 4 for the last number to make it even. So there's 6 ways to have a 2-digit number. What about a 3-digit number? Well, same thing. In order for it to be even, it has to end in a 2 or a 4. So there's 2 options there. One of those values gets picked. We then have 3 options for the first number and then 2 options for the second value. So 3 times 2 is 6, times 2 is 12. So there's 12 ways to have a 3-digit number that's even. And if we look at then a 4-digit number, same idea. In order for it to be even, it has to end in a 2 or a 4. So there's 2 options, meaning 3 options for the first value, then 2 options for the second, and only 1 option for the third. So 3 times 2 times 1 times 2 gives us 12. So now I have my 3 different cases. So what I'm going to do is I'm going to add all of the cases up, because it could be a 1-digit number, a 2-digit number, or a 3-digit number, or a 4-digit number. So 2 plus 6 plus 12 plus 12. We have 24, 32. So there's 32 ways that we could have an even number made up of these digits, assuming no repeats. How many of these numbers are less than 300? Well, let's see. We can't have any 4-digit numbers, because if it's a 4-digit number, that means it's already going to be larger than 300. So we only can have a 1-digit number, a 2-digit number, and a 3-digit number. So the 1-digit number, 2 or a 4, 2 options, doesn't matter. There's no restrictions there. It's going to be less than 300, right? Whether you have a 2 or a 4, it's less than 300. If you look at a 2-digit number, so we know it has to be an even, 2 or 4. There's 2 options, and then 3 options for the first one. Doesn't matter what the values are. In this 2-digit number, it's 2 digits. It's going to be less than 300, so there's 6 ways. Now when we get to 3-digit numbers, this is where it gets a little bit interesting. Again, we need a 2 or a 4 in the final value. So there's 2 options. However, I'm going to look at this now in 2 different scenarios because it does affect it. So what if I pick a 4, or what if I pick a 2? So if I pick a 4, there's only one way that can occur. So the 4 is taken, so that means I have now remaining 3, or 1, 2, and 3. It can't be a 3 because that means it's going to be larger than 300. So the first value can only be a 1 or a 2. So in this case, there are 2 options. So now 2 numbers have been picked in total, the 4 and then a 1 or a 2. So if I pick a 2, that means that there's a 1 remaining, and plus the additional 3 that we haven't used yet. So there's 2 numbers remaining for that middle value. There's 4 ways to have a 3-digit number that's less than 300 and even, ending in 4. Now the other scenario, if I end in a 2, there's only one way it can end in a 2, and the reason I broke it up is because now if we look at the first number, if 2 is picked to be the last number, then I have a couple options, or I only have really one option. The first value can only be a 1. It can't be a 2 because it's picked for the last one. It can't be a 3 because that would make the number larger than 300. And it can't be a 4 because if a 3-digit number starts with 4, that means it's in the 400s, so it's already automatically larger than 300. So I only have one option for the first value. So one option for the first value, it has to be a 1. 2 in the last value, or last digit, because it has to be an even number. So 1 and 2 are picked. That means I have 3 or 4. So I have 2 options, 3 or 4 for the middle one, or there's 2 ways in total. So now again, because it could be the 1-digit number, plus the 2-digit number, plus the 3-digit number that ends in 4, or the 2-digit number that ends in 2. And again, I broke it up because of that one scenario where if I end in 2, there's only one option for the first value. So 2 plus 6 plus 4 plus 2 equals 14 ways. So there are 14 ways that these numbers are less than 300, or of the even numbers that we looked at. Again, assuming that it's following the last one, which was no repeats, and using the digits 1, 2, 3, or 4. Example 3. So at an international conference, in how many ways could the flags, or could the country's flags be flown if 7, 8, or 9 countries attend? Maybe we don't know who's going to attend, but we want to arrange the flags. How many different ways could we do this? Well, depends on the different cases. I could have 7 countries, 8 countries, or 9 countries show up. So because I have those different scenarios, I have to look at each case individually and then add them up. So 7 countries, 7 flags. How many ways can we arrange 7 flags? 7 factorial. Again, assuming we're not repeating because we have one flag and it's placed, we can't reuse that flag. So 7 factorial. 8 countries would be 8 factorial. 9 countries would be 9 factorial. So 5,040, or plus 40,320 plus 362,880. Again, because it could be any of these cases, 7, 8, or 9, I have to add all of these scenarios up. So 408,240 ways in total, or the 7 factorial plus the 8 factorial plus the 9 factorial. B, if the host country is always on the far left. So here, if it's always on the far left, again, still looking at 7, 8, or 9 countries attending, we still have our 3 different cases. So case 1, 7 countries. Case 2, 8 countries. And then case 3, 9 countries. So looking at the first one, if the host country has to be on the far left, assuming there's only one host, we're going to put the far left there. Then multiplying by the next one, we have 6 options of the 7 countries. One's picked for the host, then we have 6 remaining, times 5, times 4, times 3, times 2, times 1, or essentially just 6 factorial, or 6 factorial times 1. If I'm looking at the next option, I have one host country in the far left, multiplied now by 7 remaining countries, then 6, then 5, then 4, or 7 factorial. So this works out to just 7 factorial. And in the last case, again, the one host on the far left, multiplied by, then we could look at 8 remaining countries, then 7, then 6, and 5, or essentially 8 factorial. So if we're going to go through, we have to add up all of these different scenarios and find a total. So 720 for 6 factorial, 5,040, 40,320, or basically 46,080 ways to arrange these flags if the host country always is on the far left, or it's always in that one fixed position. Example 4. So 3 players cut 1 card from a standard deck. If order is important, in how many ways could they be all hearts? So if they're all hearts, then that means we have 13 hearts in the first number, or first player, then 12 in the second, then 11 in the third. So because each player is cutting 1 card, we're assuming that it doesn't go back in. So 13 times 12 times 11, or 13 pick 3, is equal to 100 or 1,716 ways. All aces. So again, if it helps, think of the slot method. So we have 3 events, 3 players, 4 aces in the first one, 3 aces in the second, 2 aces in the third, or we have 4 pick 3. So there's 24 ways that we could pick 4 aces or 3 aces, or each player could cut 3 aces. C, all aces or hearts. We're assuming it all aces or all hearts. So looking at those 2 options. So if we look at the 2, all hearts or all aces, we have 1,716 ways plus the 24 ways. For all aces, so 17,000 or 1,740 ways. In how many ways could 11 members of a team be arranged so that the captain and the assistant captain are not together? So this might be one of those scenarios where we might have many different cases. So for example, if we had our 11 members, let's look at one case. So we're going to put 11 spots down. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have our 11 positions. Let's say the captain and the assistant captain are not together. So let's say the most extreme example, we have our captain and our assistant captain. So there's only one captain, only one assistant captain. So then that means we have 9 remaining players to fit in these other spots. So 9 options for the first, then 8, 7, 6, 5, 4, 3, 2, 1. That's only one case. We could also have the other case where the captain is in the second spot, right? So maybe we move it down. So the captain moves down to the second spot, and then the assistant stays there. Right? So that is another option that we could do. Or we could do another option after that. Let me just get through this one. So 1, 1, 9 options for the first spot. 1 captain, 8 players. 7, 6, 5, 4, 3, 2, 1. We could do this again, but move the captain down 1, and then move him down again, and move him down again, and again, and again, and so on, and change the numbers and come up with a new scenario and add it up. Then we can move the assistant 1 closer, right? Or have the assistant on the other side. So many, many different cases that we could look at. And it's not practical to go through and look at every case. So sometimes the indirect method is better. Especially in this case, because it would just take too much time to go through and try to add up all of the possible scenarios, where the captain and the assistant are apart. There's just too many possible options. Not saying you couldn't do it, just saying it's not practical. So an indirect method would be, if we're looking for the opposite of the captain and the assistant not being together, indirect method says you take the total ways and you minus the complement, or the opposite. So the opposite of them being not together would be them being together. And we have looked at this. So how many total ways could we arrange them? Well, we have 11 factorial. Right? 11 members, 11 times 10, and so on and so on and so on. Minus, how many ways could they be together? Well, you look at the captain and assistant being together. So the captain and assistant are together. There's 2 factorial ways that they could be together, one being in front of the other, either the assistant and the captain or the captain and the assistant, either way. Then you consider them as one of the groups. So we take the 2 members, we stick them together, we make them one option. That means there are 10 actual items that we have to move. So 10, 9, 8, 7, 6, 5, 4. Let me slide this down. Times 3 times 2 times 1. Because the captain and the assistant are together, they still count as one group. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 times the 2 factorial, because the captain and assistant could be in either order. We end up with 11 factorial minus 2 factorial times 10 factorial. Let's see if we can move this up a little bit too. Which works out to be 32,659,200 ways. So using the indirect method, it's a lot easier because you can imagine how many different scenarios we'd have to add up to get 32,659,200 ways. So again, the main thing from this is that we may see situations where or is included in the question, or it's implied because there are different or many different cases that we have to consider in order to kind of solve the question. So again, or in a question indicates that we add the different numbers together, or the different cases. In some cases or some scenarios or some questions like the one we just looked at, it's more practical to do the indirect method just because there are too many cases to add up. Right? So that's something you have to be mindful of. Is it easier just for me to look for the complement or the opposite and subtract it from the total number of ways? Again, not saying that the direct method is incorrect. It's just that the direct method may take a while, and you could possibly miss a scenario. You could miss a case, which would result in you getting the wrong answer. So sometimes it's easier just to do the indirect method. But again, the main thing is looking for that keyword or, which means you have to add.